Good afternoon, everyone. This is the final video of the final lesson in Physics 30, Unit 1, dealing with momentum and impulse. The final lesson was 1.5 in your note package, and it dealt with analyzing collisions that occur in what we call two dimensions using conservation of momentum. And we're looking on page 29 at example 2b. I want to explain this to you, that question 2b is identical to question 2a, which we last solved in the last video. The difference was, after we read and interpreted the question and applied the law of conservation of momentum, we developed a vector diagram and we drew a scale diagram of that vector diagram to answer the question. What I'm going to do today is go through a different method, and then we'll talk about an additional two methods. But to begin with, let's review this particular question. A steel ball of mass 500 grams is moving at 2 meters per second east. It hits and glances off of a 300-gram steel ball, which is initially at rest. The first ball moves off, that's the 500-gram ball, at 1.5 meters per second at an angle of 35 degrees south of east. Determine the velocity of the 300-gram ball after the collision. And I had mentioned in the previous video that for all of these problems that we're doing in this lesson, 1.5, we are assuming momentum is conserved, which means we know that these collisions occur in what's called an isolated system. So what we did with the scale diagram was we, first of all, got a good handle on what was going on by drawing. This is not a vector diagram. What this is just a diagram showing what's happening before and what's happening after, kind of blended into one diagram. By the way, the 1 Newton second is simply the mass in kilograms of the 500-gram ball times its initial speed. And the 0.75 Newton seconds is the mass in kilograms of the 500-gram ball multiplied by its speed afterwards. And what we said was that since momentum is conserved, those two brown vectors, which are each momenta after the collision, those two vectors after the collision have to add to give the same thing that we started off with, which is the green vector. And that led us to the following diagram. And how we solved that was we drew a scale diagram in order to find both the magnitude of that missing vector afterwards and the direction. And those values are indicated by the question marks. So what we're going to do now is the same question, but we're going to be using x and y components. And throughout this video, I'm going to be doing very little writing. Whenever you feel that you need to write something down, if I'm going a little fast, just pause the video until you catch up. Of all of the different methods you can use to solve two-dimensional collision problems, this is the method that will always work. As you get better and better at doing these types of problems, you might discover that a different method is easier sometimes, but I'm telling you, if you're ever stuck, this method is going to work. In order for you to use this method, you need to understand the following. If momentum is conserved in two dimensions, then momentum is conserved in each dimension. What that means is that if momentum is conserved in two dimensions, then momentum must be conserved in the x dimension. So the total of the x momentum before must be equal to the total of the x momentum afterwards, and momentum must also be conserved in the y dimension, which means the total momentum vertically before and after has to be the same. And what we're going to end up doing is taking this problem and breaking it into two equations. One of the equations will talk about x, one will talk about y. Most of this you have on your handout, so it's just a matter of you filling it in, but let me fill in some of the information anyway, even though it's right in front of you. So you start by organizing the information. For example, we know that the 500-gram ball before the collision has that much momentum, and it is to the east. We know before the collision that the 300-gram ball has no momentum. We know after the collision that this is the momentum of the 500-gram ball rather, but we don't know the momentum of the 300-gram ball. That's your first step, is to gather this information. I recommend a left-right chart, where on the left side of the chart you write down all of the momenta for each object before, and on the right side you write all of the momenta afterwards. Next, and I've typed up here, thinking of vectors as having x and y components. That's a little bit of a silly thing to say. All vectors have x and y components. What I am telling you here is what we need to do for this method is to determine the x and y component of each object if we know each object's momentum. For example, that 1 Newton-second east as a total momentum of that ball before can be written as an x and a y separately. We can write an x and a y component for the 300-gram ball. We can write an x and a y component for the 500-gram ball. We do not know the x and y components for the 300-gram ball, but that's going to be our goal. If we can determine these two things, we can answer the question. So what I'm going to ask everybody to do here in a minute when I tell you is to pause the video and calculate all 6, or write down all 6 of those components. The x and y component for the 500-gram before, the x and y component for the 500-gram after, the x and y component for the 300-gram ball before. A little hint with regards to the 500-gram ball's momentum after the collision: you need to determine the length of that blue arrow using trigonometry, and that will be the horizontal component of its momentum afterwards. And you also need to determine the length of that arrow, which will be the vertical component of its momentum afterwards. So I'm going to get you to pause the video, and when you have calculated those things, you can start the video again, and I will show you what I get for all of those. Okay, so first of all, starting in the top left corner, the x component of that object's momentum is 1 Newton-second east. This is a case where the total momentum of that ball before, 1 Newton-second east, is the entirety of the x component. There is no y component to anything that is east. 1.0 Newton-seconds east, which is shown at the top of the screen, is the x component, and the y component is 0. What about the 300-gram ball before? Well, it's not moving. So it has no momentum, and that means it has no momentum in either the x dimension, or direction if you like, and it has no momentum in the y direction or dimension. When I use SOHCAHTOA, sine of theta is opposite over hypotenuse, cos of theta is adjacent over hypotenuse. To find the y and x components, I get for the x component 0.614 Newton-seconds east. And it's up to you as a student to try to carry as many of those decimals as you can. And for the y component, I get 0.43 Newton-seconds, and that is south. Those directions that I've put there are absolutely critical before we go on. That you know this x component is east, this x component is east, and this y component is south. And you know the directions by looking at the little mini vector diagrams I have there. So if you had any difficulty calculating any of those, you can pause the video and give it another crack. But here's a nice summary of things. The 500-gram ball before has that much east momentum and no north-south momentum. And the 300-gram ball before has nothing in either dimension. You don't need to rewrite it this way. I'm just pointing out that this is what's going on. I've kind of boiled this down so the vector diagrams aren't in the way. These are all of the x and y's before. The 500-gram ball afterwards, we discovered that it has an east component and a south component. The magnitude of the east component is 0.614 newton seconds and the south is 0.430 newton seconds. Now, we started this by saying, oh, and the 300-gram ball afterwards, that's our goal. We need to know these two components. We started off by saying that if momentum is conserved in two dimensions, it is conserved in both the x dimension and the y dimension. So look at what we're saying here. The total x before and the total x after have to be the same. Well, if you were to add these two x's together, which are the only x's before, you're going to get the total x before. And that's going to give you 1 newton second. By the way, east is positive and west is negative, north is positive and south is negative. So when we add the x's before, I'll just show you this again. This is an x before and this is an x before. They add to give you positive 1 because that's east. When we look at the after, we have this 0.614, which is east, plus we don't know. So that's where I am getting this equation from. Just give yourself a second to think about that. We also said that momentum is conserved in the y dimension. So if I look at the total y before, that's 0 plus 0, which is going to give me 0. And if I take a look at the y after, I get I don't know plus 0.43. So this is where I get that second equation from. 0 equals I don't know plus negative 0.43. And what we need to do is solve this yellow equation that's not yellow. What we need to do is solve this yellow equation to determine the unknown x component, which will be this number in the top right screen, and solve the highlighted blue equation to find the unknown y. Well, solving these two equations that I've highlighted at the bottom, it's simple. It's like taking candy from a baby. When we solve this equation, we simply subtract 0.614 from both sides, and the unknown horizontal component is positive 0.386. When we solve this bottom equation, we simply add 0.43 to both sides, and the unknown vertical component is positive 0.43. I want to point out to you that since the horizontal component is positive 0.386, that means the horizontal component of that 300-gram ball afterwards is to the east. When we take a look at this statement that the unknown vertical component is positive 0.43, that means that Py of the 300-gram ball afterwards is to the north. What's really interesting about this method, if I can just pause the whole process here, is we never really used an entire tip-to-tail vector diagram to get this far. And we don't need to do that with all the vectors. We do need to, however, take this horizontal component and this vertical component and draw them tip-to-tail to find out what the momentum of the 300-gram ball afterwards is. Remember, both of these components are for the 300-gram ball. If you'd like, you can pause the video here and then unpause it. And when you unpause it, I will reveal the values. You need to determine both the momentum of that 300-gram ball, in other words, the length of the hypotenuse, the magnitude of the momentum, and you need to determine the angle. When I use the Pythagorean theorem, I get 0.577 newton seconds for the magnitude of the momentum of the 300-gram ball afterwards. And when I use trigonometry, specifically tangent of theta equals opposite over adjacent, I get 48 degrees. Of course, you still need to divide that by the mass in order to get the velocity, and we're getting 1.9 meter per second at 48 degrees north of east. If you were to go back and look on page probably 27 or 28 when we did this with a scale diagram, that's pretty much what we got.